Alright, in this video we'll be showing you how to calculate projection vectors. So we'll take two vectors, say 3, 1 and 1, 2. So there they are with 3, 1 in blue and 1, 2 in green. Now recall we can project W onto V by dropping this perpendicular sort of shadow from W down onto V. And this sort of calculates how much of W points in the same direction as V. And we called that the projection of W onto V, written like that. Now, how do we work out this pink vector, this projection vector? Well, every vector in this space is defined by two things: how long it is and which way it points. So if I know both the length and direction, I should be able to work out what that vector is. Okay, so let's start with the length, which we'll call L. So on the diagram, that's the length of this pink arrow here. Now recall that a dot product is very much related to this length L. Go back on that if you need to, but the dot product between V and W was defined to be the normal number product, so multiplying their lengths after projecting one onto the other, which means it's just the length L multiplied by the length of the blue vector V. Okay, now the dot product is easy to calculate. We just multiply corresponding entries and add. And the length of V is also easy, it's just Pythagoras. So on the left, we get 5, and on the right, we get L multiplied by root 10. So now the length of the projection is just 5 over root 10. And what about the direction? Well, hopefully it's obvious the direction of the pink vector is exactly the same as the direction of V. So what we're after now is the vector whose length is 5 over root 10, but which points in the same direction as V. And we saw how to do that last time. We need to first work out the unit vector pointing in V's direction, which we called V hat. And that was the vector that was exactly 1 unit long pointing in V's direction. So sort of one step in V's direction, if you will. Okay, and we got that by scaling V with the reciprocal of its own length. That sort of divided off its own length and forced it back to be just 1 unit long. In this case, we've actually done all the calculations already. It's just 1 over root 10 times V then, because we know that the length of V is root 10. So our projection must be this unit vector, okay, which again is one step pointing in the correct direction, then scaled, so it's no longer 1 unit long. Its length must be 5 over root 10, as we calculated before. Okay, so the roots cancel. After doing this a few times, you'll notice that always happens, but that's how much we need to scale V by. Now, of course, V is just 3, 1, and 5 over 10 is a half, so we get a final projection vector of 1.5 and 0.5. Now, this whole process can be packaged into a formula, which I won't bother with, so bye.